Hi everybody, welcome back to the channel. In this video we're going to be taking a look at how to find derivatives more quickly. We can't do that with every type of function that we're going to see all in one video, but at least we'll introduce that. So we're going to introduce some derivative rules, and we're going to look at how do we find derivatives of polynomials more quickly, and we'll deal with exponential functions in this section as well. So we know that we have the limit definition of a derivative that says you can find the limit as h goes to 0 of f of x plus h minus f of x all over h. We saw that in the last few videos, and that's all well and good, but that can be a little bit tedious, and there's a lot of algebra involved, and as always, we want to look for quicker and more efficient ways to be able to do things. So, fortunately, there are some nice rules that work well, and that will help us find derivative functions a lot more quickly. So, I'm going to call this section Derivatives of Polynomials. And we're going to kind of have to build up to that. So there's going to be some smaller rules that we take a look at first before we can get all the way to polynomials. Now, here's what I would recommend at the very beginning. We're talking about a lot of rules of what you're allowed to do with derivatives. Kind of like back when we talked about limits, like what are you allowed to do with limits and what aren't you? What I would recommend is that you have a separate spot in your notes somewhere that talk about derivative rules, and there's going to be a lot of them. So it's something you want to refer back to, but it's also something that you're going to want to memorize. And so you need to know very quickly in this class about how to be able to take the derivative of a polynomial. How do you take the derivative of exponential functions? How do you take the derivatives of trig functions, of logs, of combinations of those different functions? And so a lot of different rules that you'll see and that you should have in your notes, kind of in their own separate section, but definitely also things that you're going to want to memorize really quickly. Okay, so let's go ahead and just jump right in to some rules. Some are a little bit more straightforward than others. We're going to start with ones that are some ones that are pretty basic. So just as a reminder about some notation here, I'm going to write d over dx. We saw this in the last video, that means the derivative of something with respect to x. And so I could write it like this, just as a reminder about some notation, that d over dx of something is kind of like saying, take that function, that something, and take its derivative. You could use prime notation on the right, or you could use the d over dx notation on the left. So the derivative of f of x is also written as f prime of x. So either way, I'm going to use the notation on the left for this video, or for a lot of the things in this video at least, just so that we kind of get used to that and get comfortable with that. I think that notation of d over dx takes students a little bit longer to kind of get used to than just using f prime. And so I want you to be comfortable with both of those, so I'm going to kind of model that for you in this video. Okay, so and in a couple of places I'll kind of show you what it looks like with the other notation as well. So I'll call this rule number 1. We don't need to label these as far as numbers necessarily, but I just want you to know that we're jumping right into the rules right away. So what happens when you take the derivative of a constant, which I'll call c? Okay, and I'll go ahead and put that in parentheses just so I try to put whatever your function is in parentheses, just so that's clear. In other words, if f of x equals c, what's f prime of x? Okay, and so you can think about this. Remember that a derivative means the slope of the tangent line. If you just have a function that's y equals c, that's just a horizontal line. In other words, what's the slope of the horizontal line? It's actually 0. Okay. Because that's the slope of that. The slope of the tangent line is just the slope of the line that we have there. What about if we have the derivative of just x, like f of x equals x? Well, that's this function right here. That's this line. What's the slope of that line? That's just 1. Okay. And so starting out pretty basic here, but we will see problems that have these, probably not necessarily just this function, but they'll have pieces where you'll have a constant as a part of your function, and we need to go back to this. Or you'll have pieces where you just have an x in your function, and we need to go back to that. Okay. The third rule that we're going to look at is actually a really important one. So even though these two are really straightforward at the beginning, the next rule is going to be one that we'll kind of take a look at. We'll prove it'll be one of the bigger results here in this section, and then we'll kind of combine some other rules together as well to get a little more complicated. So let's go ahead and go over here, and we're going to take a look at something called binomial expansion, or maybe you've heard of a binomial theorem before. And the reason why this is going to be helpful is because the next thing that we're going to look at is, what about if f of x is equal to x to the n? Okay, I wouldn't quite call this a polynomial at this point. This is something that's probably more commonly referred to as a power function. In other words, there's no coefficient out front. It's not plus other terms. It's just x to the n power. Okay, could we go ahead and find f prime of x when you know that x to the n is your function? And if you go back to that limit definition of the derivative, we'd have the limit as h goes to 0 of x plus h to the n. Okay, the h and the n kind of look alike, so I got to be a little careful. So x plus h raised to the n power minus x to the n power all over h. That's your limit definition of the derivative. Okay, and if we could simplify this, then we could find the derivative, find f prime of x. The problem is there's no numbers in this. There's x's, there's h's, there's n's, but all of those are kind of arbitrary, either variable for the x or an arbitrary constant for the h and the n. Okay, so why do we need this binomial expansion? Well, we need to know how to be able to handle x plus h raised to the n power. And what we're going to look at, what we're going to kind of hone in on is, if you look at every single row in this binomial expansion, we are going to look at kind of this second term right there, okay? Because if you expand out x plus h to the n, you may have seen this table before, by the way, or the triangle, or sometimes it's called Pascal's triangle. There's a lot of different patterns that show up in here, but basically what we're going to try to do with this is we're going to try to say, can we break down this derivative and kind of simplify it, even though h and x and n are pretty arbitrary here. So x plus h raised to the n power, if we try to kind of expand that out, even though there's no numbers involved here, the first term is going to look like x to the n. Okay, that's like on the very left side, the very first piece in every row just looks like a to the third, or a to the second, or a to the fourth. There's no b's, there's no coefficient, it's just a to whatever power. But a, that's because a is the a plus b. Ra in our example is x. So x to the n power, the second term, when we try to expand all this out, is going to look like, if you look at the patterns in here, it's going to look like n times x to the n minus 1 times h. And kind of the idea here is, if you look at in the binomial expansion, let's kind of hone in on one row. I'm going to look at like the third row here, for example. Okay, that third row, you got a 3 in front because that's what the exponent was. And so in here, you have this n in front because that's what the exponent was. And then notice that the a has a second power on it. So the x doesn't have an n power, it has one less than that. And then h actually has a first power on it. If it was an exponent, we don't usually write the first power, but h would have a first power on it, okay? And so the next element, when you expand all that, would look like some other coefficient times x to the n minus 2 times h squared. And you could kind of keep on going with this. You're going to be adding a whole bunch of stuff if you were to expand this out. And eventually you get to the very end, which would look like h to the n power and then minus x to the n with all of this. And this is all on the top of the fraction. That's maybe not written out the very, very best there. But the idea here is this: if you were to try to look at that entire row and expand all that out, you're going to have an x to the n in the front and a minus x to the n on the end. Hopefully remember in the last video, we said that everything that originally showed up in the f of x should cancel after you've kind of expanded everything. Okay, so we have an x to the n cancel with an x to the n. Now, there's a lot of stuff in here, and notice I have this dot, 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 which means I don't know how many terms there are. It depends on what n is. But look at the terms that are going to have an h in them. They're all going to have an h in them. Every single term here, here's a term, there's going to be a whole bunch of terms. Every term has more than one h in it, because you're going to have an h squared, and then the next one's going to be an h to the third, and an h to the fourth, an h to the fifth, and h to the sixth, keep on going, all the way up until this h to the n over here. Okay, and so I'm kind of butchering the diagram, but the thing is, it's actually all going to go away, because think about what we've done in our last problems is after we got to that point, we factored an h out of everything that has an h in it and canceled that h with the bottom. So like cancel this h and one of those and one of all the other h's and one of those h's and cancel that one with the bottom. And what you're left with is going to be something that looks like n times x raised to the n minus 1 plus it's going to be there's something in front and then x to the n minus 2 times h plus, and you're going to have all these other terms that all have at least one h in them. All of these ones right here all have an h in them. Well, now there's no more h on the bottom because we canceled. And what's going to happen after we cancel that is now we can let h go to 0. So all of these other terms are all going to be 0. They all don't matter. The only one that's left over is this one right here. And so what this is going to give us is just an n times x raised to the n minus 1, and that is our derivative. That's what f prime of x is equal to. And so when we look at this, let me pull up another board here. Really what all that says with the binomial expansion there is if you start out with a function that looks like x to the n, what its derivative is going to look like, okay, f prime of x, its derivative is going to look like n was down front, and then x raised to the power of n minus 1. So you can think about what this means. In fact, we didn't, I'm trying to remember if we looked at examples like this. We didn't look at an exact example of this. But this means that if your original function is x squared, okay, or I tell you what, let me use that d over dx notation. I said I was going to use that a bit. So if we take x squared and we take the derivative of that, let's see, the n up in the exponent is a 2. That should drop down in front. And so we should get a 2 down in front. And then the n minus 1 says your exponent is going to lower by 1. So you're still going to have an x there, but now instead of an x to the second power, it's going to go down by 1. Now you're going to have an x to the first power. Or, by the way, that's just 2x. Okay, what does that mean about if you have your original function as x to the third? Well, then you're going to have a 3 out front because that was the exponent. And then you're going to have an x to the power of something that goes down by 1. So 3 minus 1, you get an exponent of 2. Okay, what happens when you take the derivative of x to the fourth? You're going to get 4x to the third. And so on and so forth. And this works for small numbers, big numbers. It works. It's actually going to work even when your exponent is not a whole number, even if it's not a, or maybe I should say positive integer there, of it doesn't just work when you have a value that's kind of nice and round. It also actually works when you have decimal exponents or fraction exponents that get a little bit weird. So we'll see that as well. But like, let's say you have something like the derivative of x to the, I don't know, 57th power. Okay, this means that you can find the derivative really easily without having to worry about x plus h to the 57th power. You remember that limit definition? I don't know if anybody would want to do that by hand. Using that binomial theorem, it means you got to FOIL something out like 57 times. That's ridiculous. But using this, we can quickly say, oh, you know what? The derivative then should be 57 times x to the 56th power. So this is a really nice way to be able to calculate the derivative of a power function, and then we'll build this up with some other rules to get to kind of all polynomials. So this is pretty nice at this point. So I would call this the power rule, okay, that says that when you have f of x as x to the n, f prime looks like n times x to the n minus 1. Again, I said you want to have a kind of a list of different derivative rules on here. You can name this one. This one is an important enough rule to kind of get a name, called the power rule. This is one we're going to come back to a lot. You should get really comfortable with this as quickly as you can, taking derivatives of exponents or functions with exponents in them.